Good day. I would like to present to you integrated modeling and analysis of electrified railroad operations and traction power systems. Let's talk a minute about modeling rail systems. We're going to develop a dynamic physical model for a rail system. So we create a physical track model. We're able to evaluate the elevation of the track, which is a significant parameter mechanically, and considerations of rail system types is something that's important. So we would look at a conventional versus a high-speed rail system. And we're going to talk about power systems. So we would integrate our AC or DC electrification power system into this discussion. So, why do we do this? We want to use the model as an engineering design tool to evaluate the performance dynamically of our railroad. We want to simulate the train physics, the mechanical energy of the train physics, the resistances, the braking, the regeneration, all this dynamic mechanical energy. We're going to use a very powerful tool, the ETAP software, that has a module, the eTraX module, that allows us to define a dynamic mechanical model for railroad systems. And we do this so that we can study the system behavior of the train for performance, but also to validate design data. So what's the importance of this? What value do we get out of this? Well, we can utilize the models to study and optimize the physical design. We can consider adding more trains to a particular route by controlling the speed and evaluating the physical dynamics of the train. And we can take the mechanical model, and with this software, the ETAP software, we can integrate the electrical tools provided within ETAP. And we can do a dynamic mechanical analysis that allows us to integrate the electrical tools within ETAP and study the electrical performance of the traction power system as well as the mechanical system. And we can do this analysis simultaneously. So eTraX allows us to develop a dynamic train model that can be integrated to evaluate the electrical power requirements. And in this manner, we can study the system behavior mechanically and electrically, again, to validate the design and optimize operations. We can look at capacity, we can look at time schedules, and optimize the performance of the railroad. There are other value streams for doing modeling. For instance, you can examine infrastructure failure contingency analysis, such that if your system experiences a failure, you can study different impacts from the failure. How does that impact your operation of the railroad? What restrictions might have to be applied on the railroad if there's a failure? What limitations to propulsion you might have to implement? If you're in need of conducting modifications, construction projects to the railroad, there may be contingencies that you would like to evaluate in order to facilitate construction. We'll talk about a project that I was involved in that we applied that analysis using the ETAP software and eTraX modules. The eTraX module allows you to look at train delay contingency analysis and also to do mitigation analysis other value streams for the eTraX module is that you can compare different rolling stock and the performance of the different rolling stock. That way you can evaluate energy consumption and evaluate different traction power supply designs based on energy consumption parameters and the variations of power consumption from different rolling stock. You can also evaluate the effect of energy storage and regenerative braking. The ETAP software with the eTraX module allows us to speed model development. And when schedule is important and you need to have speed on the basis for a project, these tools are very valuable. You can integrate and import multiple third-party electronic data. That way you can develop your model very quickly. There's a GIS tool that allows you to integrate GIS mapping data to validate the dimensions and elevations, curvatures of the terrain profile. And with the integration of electrical and mechanical analysis, the ETAP software allows you to manage and analyze multi-dimensional databases. So in eTraX, we develop a model that's a catenary and rail system model, and then we can use the various modules in addition to the eTraX module, which gives us the load flow. We can utilize arc flash modules, protection and coordination modules, and short circuit modules to analyze multiple multi-dimensional databases. The ETAP software has very complex relay coordination evaluation tools, and that becomes a very important aspect in developing a quick model that can be deployed for the user. So I'm going to look at a project that I was involved with, and we had construction constraints. The client came and said, hey, we need to rebuild our supply station for a 2x25 railroad, and we have to build the new substation in exactly the same spot as the existing substation. So that's quite challenging. Sometimes we build overhead. In this case, we couldn't do that. We had a very small footprint. And so what we did is we split the system in half. This particular system, 2x25 system, had 4 20 MVA supply transformers, 2 that fed to the east and 2 that fed to the west. And when we split the system in half, we put the entire railroad section that we were working with on 2 20 MVA transformers. So now we only had 50% of our power capacity feeding the entire railroad. And the concern here for the client was that if there was a failure, we needed to look at contingencies on the railroad during construction. The construction was going to be a 2 to 3 year long process. So the modeling and analysis was performed to ensure that if there were any kind of failures, that we had contingency operational criteria ready to go if we had to limit propulsion or change scheduling. So here we reconfigured and demolished and rebuilt the supply station, and we reconfigured, demolished, and rebuilt the auto station. And in order to do that, we had to use some temporary power. So we needed to analyze temporary protection and control and temporary conditions on the supply and auto transformer station and buses. So this is a picture of the site here. You can see this is a temporary supply 230 kV that was built for the project so that we could demolish the 230 here. So you can see here, there's a space where half of the 230 was demolished. And then this other 230 half, 230 kV half of the substation is in the process of being demolished. And the station is being fed from this temporary 230 kV that goes back to these two supply transformers, which are going to remain. These supply transformers at 230 kV get demolished, and then this half of the auto station gets demolished. You might ask how we were going to run a railroad with half the auto station. So this particular client decided to purchase a mobile auto transformer and mobile traction power breakers all on one trailer. This mobile substation was installed, which required us to do further evaluation on the load flow of the revised impedances of the system, as well as looking at the contingencies in case there was a failure while we're feeding in this compromised design state due to construction and upgrades. And this protection and control system had to be evaluated. So this project had some aggressive schedule components. We were able to integrate third-party data and also use the ETAP model, electric model, to validate old hand calculation data. We integrated multiple third-party electronic data to validate original short circuit and load flow data that had been updated over the life of the railroad. So all of that original hand calculation data and integrated multiple third-party load flow data was used to calibrate, validate, and calibrate the model. And once we had an agreed upon model and everybody was happy with the validation, multiple failure scenarios were defined, and then case studies were run to evaluate the performance, electrical performance and mechanical performance of the railroad. Can we still operate trains if we have a failure in the compromised construction state? Do we need to put limitations on propulsion? Do we need to feed the railroad from alternate supply stations? This was the analysis that the ETAP software and the eTraX modules allowed us to do in a very short period of time to allow this project to move forward and to allow the owner to be comfortable with contingency scenarios. So, we looked at 3 failure contingencies, 4 different model topologies. We looked at the existing model, a phase 1 construction model, phase 2 construction model, and a final design model. Each phase had 126 short circuit cases. So that's a lot of analysis. The ETAP integrated features with eTraX allowed us to go back and forth very quickly to do the short circuit case studies and evaluate the impact on load flow. So we took a legacy model that was there, and we were able to validate that model, but also show the client how accuracy of the new computerized model techniques, and slightly improve the evaluation capabilities. And new equipment was added into the model. So we were able to compare the original design to the new equipment model design. The protection studies that were done included line distance, differential, and directionality, 67 elements. So the project had an aggressive schedule. The objectives were met. How were the objectives met? Well, we knew we needed to get speed on the bases, so we sat down and negotiated expectations. We were able to identify confidence factors with the management relative to the long history that ETAP has in the marketplace. And by setting proper expectations. The technical expertise of the engineering folks at ETAP was evaluated. Um, we performed or formed preemptive validation teams with a handful of consultants, the subject matter experts at the railroad, and with various folks that had different skill sets at ETAP. We developed the train load flow voltage profile with eTraX, and we developed a power system model to evaluate short circuit and coordination studies, and imported third-party data that allowed us to move very quickly into the analytical phase, model development, and model validation. So we developed an extensive 2x25 traction power railroad model, validated low flow results against original engineers' calculations, validated short circuit results against original engineers' calculations, and then validated low flow results against the most recent computer analysis. We used GIS interface that speeded the physical railroad modeling. We developed a dynamic electromechanical model. This requires less data, so that accelerated our modeling for the railroad. We used Scenario Wizard, which is just a powerful tool within the ETAP software to quickly analyze multiple scenarios for different case studies and failure analysis scenarios that were defined that we wanted to evaluate their impact on the system. It was a construction or a temporary configuration of the railroad. And we validated the model against not only original calculations, but we went out and took empirical data during the construction phases to further give confidence to the owner that, you know, the modeling tools and the data that we're gathering in the field were aligned and providing similar results. You know, we took relay event data from the temporary relays and some of the new relays. We installed some high-speed power quality meters and gathered time plot data and momentary waveform data to look at events and use that data to optimize and validate the model, and also to provide input to the protection study for settings. So there was a collaborative effort to define and review the empirical data for the enhanced model validation. The client was very diligent in bringing peer review engineers to the table to review independently the assertions of the ETAP software to confirm that the performance of the ETAP modeling could reflect the original design and be validated against the original models and validated against empirical data. So it was a very much a collaborative effort and an independent peer review that went into the modeling process. Justifications for model deviations where there was differences in the model results led to validation integrity, further validation integrity to give the owner and the peer review engineers additional confidence in the capabilities of the tools. And then we performed collaborative review with the owner's engineers and the owner, and documented the results in reports, gave the opportunity of multiple teams to provide input to make the product and the results better. So we needed to analyze multiple scenarios here. We used the Scenario Wizard to do that. We had to analyze a phase 1 construction design or configuration of the railroad and a phase 2 construction configuration. And this provided critical insight to understand, limitations of the railroad propulsion limitations during construction, and to evaluate additional contingencies that might need to be considered during construction if there were contingency failures. The eTraX allows us to apply a dynamic inclination and declination during validation of the train schedule and voltage profile for worst case scenario analysis, which was important during the construction. We needed to identify that if we had a failure during construction, did we need to switch over to an alternate supply, or did we need to limit propulsion and limit operations? eTraX incorporates a GIS tool, so that allowed us to move quickly and speed up the modeling and then get to the analysis of the data. And the GIS tool allows the physical data to be more accurately depicted in the modeling. The ability to integrate eTraX as a module with the ETAP software or the other modules within ETAP allowed us to expedite analysis of multiple short circuit case studies that needed to be done for this project. Those cases needed to be done to look at the load flow and also revision of the protection coordination settings that were affected by the construction. ETAP imported, developed legacy line differential relays very quickly, and also inputted the new microprocessor 61A50 base relays, modern technology. We evaluated and inputted distance protection elements, directional elements, and we inputted the empirical data such that we could evaluate and refine, calibrate protection settings. That's the end of the presentation on eTraX, mechanical modeling, and how that can be useful in integrating ETAP's power system modeling to speed up development of modeling and perform complex analysis of traction power systems. Thank you.